The old Pascal's triangle with row 0, row 1, row 2, row 3, and row 4 represented there. Interesting. We can write the numbers that are written down on Pascal's triangle in NCR notation if we feel like it. So, for example, this one here, that's 4C0, that's 4C1, that's 4C2, that's 4C3, and that's 4C4. And all those numbers can be written that way. Let's just go above as well and do 3C0, 3C1, 3C2, and 3C3. We know the stock standard way you start writing out Pascal's triangle is to look at two numbers, and then the one, if you add them together, you get 10. So that'll be the number that'll go symmetrically below. 6 plus 4 is 10. 4 plus 1 is 5. 4 plus 1 is 5. So we can write in the next row and so on. So that would mean that these two numbers here, 3C1 and 3C2, have gone together to make 4C2. 3C1 plus 3C2 have gone together to make 4C2. So we can write out some patterns in general terms that we notice from that. If you let the first one here be n, this would be saying n, c, and if you pick a number, say r, then the next one along would be n, c, r plus 1, and that will be the same as n plus 1, c, r plus 1. So these numbers were the same, so keep them the same. These two, if they're n, then this is 1 more than it, because 1 more than 3. So you can actually write out what appears to be a rule that's happening in Pascal's triangle. That's not the only way that you could have written that rule. Someone might have gone, no, I'm going to call this 4C2, I'm going to call that NCR. Well, if that's the case, then this is n minus 1 CR, because they're still the same, 2, 2. And this is n minus 1 C, R minus 1. Same rule. It just depends what you want to call n, where you want to start with n and with r. So they come out of Pascal's triangle, and we know from our assignments that there's all types of rules to do with the simplex numbers and Fibonacci numbers and the hockey stick theorem, all the powers of 11, all sorts of things in there where we can write out general rules in terms of the NCR notation. So today I want to talk about how you might be asked or how you might go about proving a rule like those two rules. So let's take this first one that we gained. Let's take NCR plus NCR plus 1 equals n plus 1 CR plus 1. Let's take that as the rule that we've been asked to prove. It has a left-hand side, an equal sign, and a right-hand side. So we can start with either side, do some manipulations, and end up with the other side. So I might start on the left and see if I can make that equal to the right using mathematics. So the left-hand side of this is equal to NCR plus NCR plus 1. In factorial notation, that's n factorial on n minus r factorial times r factorial. And this one here is n factorial on n minus r plus 1 factorial times r plus 1 factorial. It's a little bit tedious writing it out, but that's the way you've got to do it if you're going to be proving that this rule is true. So you need to know how to turn NCR into factorial notation. And we've done that in other lessons. It could be a time now that you revise that. But once I've written these out, I need to make a common denominator. I need to appreciate, though, that r plus 1 factorial is just r plus 1 times r factorial. We've talked about that also in other lessons. R plus 1 factorial is r plus 1 times r factorial. And similarly, this here, it says n minus r minus 1 if you expand that. N minus r minus 1 factorial. And the reason I point that out is this one here, n minus r factorial, is just n minus r times n minus r minus 1 factorial. This means that this fraction here and this fraction here can be put together with common denominators, but I'll write them out so that you can see how we're going to go about that. This is r factorial times n minus r times n minus r minus 1 factorial. This one here is n factorial on r plus 1 times r factorial times n minus r minus 1 factorial. So we can see what we need to do now to make a common denominator. Each of the denominators already has that in it. Each of them already has that in it. So the things that we need to do is we need to make sure that both denominators have that and both denominators have that. And then we can have a common denominator. So this first fraction, the n factorial on r factorial n minus r n minus r minus 1 factorial, we need to multiply that by this r plus 1 on r plus 1. Now this denominator will have an r plus 1 in it here, which is required because the other one does. Plus, now this one here, this n factorial on r plus 1, r factorial n minus r minus 1 factorial, it's going to need to be multiplied by what it doesn't have, which is n minus r. So now the denominators are the same. The numerator here, we've got n factorial times r plus 1. We've got n factorial here times n minus r. And the common denominator is r plus 1 factorial, because r plus 1 times r factorial, r plus 1 times r factorial is r plus 1 factorial. N minus r times n minus r minus 1 factorial, and n minus r times n minus r minus 1 factorial is just n minus r factorial. Just need to pull this up so we can go over the page. So on the top line, if I expand that out, well, if I factorise it, I have n factorial into r plus 1 plus n minus r. And on the bottom line, I have r plus 1 factorial times n minus r factorial. So r minus r is cancelling, and I get n factorial n plus 1 on the top line. And on the bottom line, I end up with r plus 1 factorial and n minus r factorial. Now, this is a little bit of thinking here, but n minus r factorial, is that the same as n plus 1 minus r plus 1 factorial? And the reason I ask that, and I'll show you the original question that we're trying to answer. The reason I ask that is I'm trying to show that this left side equals the right side. And the correct way to write that out is n plus 1 factorial on the top line, which this is going to give us. And on the bottom, we know that you do n plus 1 minus r plus 1 factorial times r plus 1 factorial. So if this equals this, we're going to be able to get what we need. Does it? Well, let's just expand that out. This would be n plus 1 minus r minus 1, which is n minus r factorial. So yes, n minus r factorial does equal what we're after there. So I'm going to rewrite it like that. I've got n factorial. Well, actually, n factorial times n plus 1 is n plus 1 factorial, but I'll rewrite that in the next line. And I've got r plus 1 factorial. This is n plus 1 minus r minus 1 factorial. I'm just writing that line in now. So this is n plus 1 factorial on the top line. And on the bottom line, it's r plus 1 factorial times n plus 1 minus r plus 1 factorial. Okay. Now, just need to move this up a little bit. This equals n plus 1 c r plus 1, which equals the right-hand side of what we're trying to prove. Because as you recall, what we're trying to prove had n plus 1 c r plus 1 on the right-hand side.